Everyone, I'm Miguel Ibanez. I come from the Nanoparticles Trapping Laboratory located in Granada and led by Professor Raul Rica. And I want to talk to you today about an asymmetry we have discovered between heating and cooling trapped nanoparticles. I invite you all to have a look to our new recent publication in Nature Physics with this group in collaboration with the Mathematical Biophysics group located at the Max Planck Institute for Multidisciplinary Sciences and led by Professor Alias Godek. Anomalous relaxation phenomena have caught so much attention from the scientific community. Despite seeming to be novel, the truth is that they have been known since ancient times. I want to introduce this talk with this Aristotle's quote. Many people, when they want to cool hot water quickly, begin by putting it in the sun. He was referring to the Mpemba effect, without actually knowing it, by which hot water cools down faster than warm water. Linear response theory traditionally predicts a monotonic behavior in systems perturbed slightly from equilibrium, with its relaxation dynamics directly correlated to initial temperature differences. However, in scenarios with high temperature contrasts, initial conditions...
Miguel, your slides are not changing.
What?
Your slides are not moving forward.
Oh, sorry. But are you seeing my screen now?
We're seeing you have screen, but only the first slide.
Oh,
there we go.
now
you're moving forward. Okay.
Yes.
So maybe I can share my whole screen. Can you see I mean,
Yes.
you don't see the different slides?
We are seeing now your fourth slide.
Slide 4.
And now?
Maybe no. Unshare your screen and share your screen again.
Okay, one moment. So the whole screen.
Mm-hmm.
Are you in presenter mode? Or whatever mode you're in, actually?
Now?
Yeah.
Yes. Now it's working. Okay,
that works? Sorry.
We saw the first screen before, so unfortunately, you've only got a little bit more than 7 minutes. Go for it. We'll have fewer questions.
Okay, so I was saying that when we are very far from equilibrium, initial conditions play an essential role in the relaxation phenomena, leading to the so-called anomalous relaxation phenomena. So focusing on a problem we're going to analyze, we studied the position of an overdamped trapped Brownian particle in a harmonic potential. As you know, its position is a random variable, which probability density function satisfies the Fokker-Plan equation I wrote here. In the right, I show the experimental evolution of a histogram of a trapped Brownian particle when the bath temperature changes from a hot to a cooler value. And we see that it confines in time. So as the PDF changes depends on X and T, we can think that the system evolution traces a curve in the manifold of distributions. So if a curve is traced, could we apply a sort of kinematics to this type of problems? Could we talk about distance, speed, and length? That's what we try to do. So let's think we have initially a state P0 and we want to go to a final target state PF. And during the evolution of the system, this system will trace a curve, as I told below, when we apply a certain protocol to our system. As we do in conventional geometry, we can define or choose a distance from the state at time t with respect to the final target state. We chose the relative entropy or Kullback-Leibler divergence. Although it is not mathematically speaking a distance because it is not symmetric under a change on these arguments, it can be proven that it acts as an excess of free energy between the state at time t with respect to the final target state. Once we have chosen the distance between the instantaneous state and the final state, we can talk about speed by simply expanding the distance between two very close states. By doing so, we obtain the so-called Fisher information metric. And by simply making the square root of this Fisher information, we can define the instantaneous velocity at time t. And finally, by simply integrating this square root of I of t, we can define a length traced by the system until time instant t. With these three ingredients, distance, speed, and thermodynamic length, we have our framework we call thermokinematics. Once we have established our theoretical background, here's our claim, that heating a Brownian particle trapped in a harmonic potential is always faster than cooling it. We proved it both experimentally and theoretically. Firstly, how did we create a harmonic potential in 3 dimensions in space? By means of an optical twister device. If you don't know what's an optical twister device, it consists on a laser beam which is tightly focused on a single point in which we locate the particle to study. We trap this particle in water and between 2 electrodes, and by means of the gradient forces, we can create a harmonic potential in 3 dimensions in space. We created this uniform electric field between the 2 electrodes and the particles because we wanted to apply a white Gaussian noise to this particle in order to mimic the effect of a higher temperature than the bath, and to have a precise control on the temperature the particle suffers. And finally, to create these quenches between hot and cold temperatures, we multiply this white Gaussian noise, this electric white Gaussian noise, by a square signal. And I can show here the effects on the particle when we change instantaneously from a hot to a cold temperature and vice versa. So we proved that heating is faster than cooling, mainly in 2 different situations. The first one involves 3 different temperatures: 1 cold temperature, 1 warm temperature, and 1 hot temperature, chosen in such a way that the distance from the cold to the warm is initially the same as the distance from the hot to the warm state. In all the plots I'm going to show, the single dots and squares represent the experimental data, and the solid lines represent the theoretical predictions. And I also chose the red color for heating and blue for cooling. Firstly, we analyzed the behavior of the distance with respect to the common warm state, and we saw that this distance was always lower in the heating case than in the cooling case. Consequently, we can conclude that heating was faster. We also saw the behavior of the speed and thermodynamic length during the evolution, and we saw that initially the speed for heating was always higher than in the cooling case. And finally, we also saw, as I said, the behavior of the thermodynamic length during the evolution divided by the total value of the curve, what we call the degree of completion, a quantity that goes from 0 to 1. And we saw that in the heating case, this magnitude reaches its final value faster in heating than in cooling. The most striking fact is that the curve during the heating process is always longer than in the cooling case, although this curve is traced faster. And the most strikingly situation we also analyzed was the one that considers a single pair of temperatures, 1 cold and 1 hot temperature. In this case, we cannot talk about a Kullback-Leibler divergence because we don't have this a common reference state, but we can apply the aforementioned framework of thermal kinematics, and we derive also that the speed in heating was faster than in cooling, and the degree of completion reaches the final value faster in heating than in cooling. This reveals that the asymmetry of heating and cooling processes was a very fundamental behavior in nature. And to conclude with, the take-home messages could be that heating and cooling are inherently asymmetric processes. Also that the equilibrium paradigm breaks down when we subject to the system a very strong temperature contrast, and also that thermal kinematics provides us a novel insight into transient dynamics of stochastic processes. And that's it. Thank you.